Okay, welcome to day 5. Today we're going to talk about compositions. We talked about compositions a little bit at the end of last class, and basically a composition is when you put a function into a function. So two ways to write it is like this, f of g of x, or we use that little open circle, that's called a composition circle. And we read that as g composite f of x, but that is the same thing as g of f of x. The whole idea with composition, we're putting a function into a function. Order does matter, it's very important, and the function that's closer to the input is always done first. So the idea is that we're going to use the first result as the input for the second function. So we have a couple of examples, and the first one that we'll do will be what you did in Algebra 2 a lot, where your input is a number. So the first thing I have to do for this one is g of 2. So g of 2 is equal to 1, and now I'm going to use that result and plug that in the second function, which is the f function. And when I do all that, I get 0. So I write my final result, f of g of 2 is equal to 0. Now remember, I said order does matter. So over here, I think I'll use pink. I have to do f of 2 first because that's closer to the input. F of 2 is equal to 2 squared plus 4 times 2 minus 5. I get 7. I'm going to use that result and do g of 7. I get 11. Now I have g composite f of 2 is equal to 11. And if you notice very carefully, because order does matter, that f of g of 2 did not equal g of f of 2. Order does matter. Now we're going to use variable x as our input, so I have to do that first. So this becomes g, f is just x squared plus 4x minus 5, and this whole thing that I'm underlining becomes the input into the g function. So that's 2 times my input of x squared plus 4x minus 5 minus 3. And if I distribute and subtract a 3, I get g of f of x is equal to 2x squared plus 8x minus 10, but minus 3 is minus 13. Now I have to go the other way. This is going to be a little bit more work. So I have to do g first, so this becomes f of g, which is 2x minus 3. And the 2x minus 3 becomes the input for every time you see x. So it's 2x minus 3 squared plus 4, 2x minus 3 minus 5. And if I expand this binomial, we talked about this briefly, that's 4x squared. 2 times negative 3 is negative 6, times 2 is negative 12x plus 9. Distribute plus 8x minus 12 minus 5. So I get a final result of, I'll do it in black, f composite g of x is equal to 4x squared minus 4x minus 8. And again, if you notice, g of f of x does not equal f composite g of x. That is what's going to happen every single time. And if they do, something special is occurring, but they should not equal each other. So now I'm going to apply it to a table. if you notice, I've been given the condition that the function r is p of q of x. I have that here. That means first I do p of x, and then I do q of x. So when I start, I'm going to start with x equals 1. That means I'm trying to fill in this square right here. Well, according to my model, I have to do, start at 0, I have to go to, oh, I wrote this backwards. It's going to happen sometimes when I make videos. First, I do q of x, and then I do p of x. So going back to what I want to do, it says when I start at 0, I have to go to q of x, and I get a result of 5. Now 5 becomes my new input, because the first result becomes the input for the second function. And now I have to do the q, and that q result is when x equals 5, q is 4, and then it comes all the way here, and my final result goes right in here. I'll do it in pink. 4. Now usually what I do is follow my finger. I go, I'll do it very lightly in green. Start at x. I'm trying to fill in the bottom square. Start at x equals 1. When I start at x equals 1, I go to q. I get 2. 2 becomes the input. X equals 2, I go to p. P equals 5. And that goes here. And there's my 5. If I do the same thing, I start at x equals 2. I go to q, which is 3. I go to x equals 3. I go to p. And that answer is 2. 5. This answer is 2. I start at 3. I go to q. My result is 1. I go to x equals 1. I go to p. I get 0. I start at x equals 4. I go to q. Q is 4. 4 becomes an input. So x equals 4. P equals 3. And then finally, I start at x equals 5. I go to q. Q is 8. And then I have no place to go on the table because there's no x equals 8. So since I have no place to go, this one is undefined. So using this table above, I'm trying to find when does p of q of x equal 4? Well, that's the last row, and this is the last final result. So it wants to know what x value did I have to do to get 4 as a final result. 4 as a final result. Well, that one was x equals 0. And then over here, I want to do the same thing. I'm going to get 1 as a final result, and I don't see 1 anywhere as a final result, so there's no solution to this one. Okay, we've done equations on the first part of the first page. We did a table on the bottom of the first page. Now we're going to do a graph. So the composition of the same thing. I go in order, closer to the input. What I like about this graph is that all the x values that are integers, they have y values that are integers. I made the g graph highlighted in pink. I did f graph highlighted in green. So the first thing I have to do is g of 1. So I go to 1. I find the g graph, and I find that result is 3. So now I have to do f of 3. So I go to 3. I go to f graph. I see that result is 2. So this result is equal to 2. I'm going to do the same thing over here. I have to go to f of 1 first. I go to 1, and f in the green is equal to 2. I have to do g of 2. I go to 2 on the x. I go to the pink graph, and I see y is equal to 2 there. So this is also equal to 2. Now the next problem is a little bit more difficult because these 4's here are y values. So I need to work in reverse. I'm given the final y value of this composition. So when I work in reverse, I'm working with the f function first. So in my mind, I say I have, let me move this up just a little bit. This says f of g of x equals 4, or better yet, f of some input value is equal to 4. So I go to y equals 4, which is right here. I go to the f function. I find that input is 2. So that input value was equal to 2. But that question mark, that unknown, was the g of x. So I could say g of x is equal to 2. Again, that 2 is a y value. So I go to 2. On the y value, I find my g graph, which is the pink one, and that input is x is equal to 2. Now I'm going to pick. For this one, I'm going to do the same method. I'm going to call, I have to do in reverse order, so I have to say g of some input value is equal to a y value of 4. So I go to y equals 4. Right at the top, and the g value, that is x equals 0, so I have my input value of 0, but that input was f, so f of x is equal to 0, so I go to 0, which is at the bottom, and I see the f graph hits y equals 0 twice at x equals 0 or x equals 4. You could have two x's, you can't get two y's. Okay, so we're going to play symmetry of even, odd, or neither, and I think we understand that an even function from a graph, something like x squared, looks like this. We have something special going on, that this point xy has this mirror point at negative xy. So if you look carefully, I have opposite x's, but the same y value. And then I could do the same thing for an odd graph. I'm going to use x cubed as an odd graph. I have this point here, xy, and its mirrored point over here is negative x, negative y. So when something is odd, is that when I have opposite x's, I have opposite y's. Okay, that's very important to understanding the difference between even and odd. Even means I don't care if I have a positive x or negative x value, my output or y value would be exactly the same. And an odd function means that when I have opposite x values, I have opposite y values. So how do we apply this to a table? Well, let's make the note that f is even and g is odd. Let's do the even one first. So right here I have when x is 3, y is negative 4. So when I come away over here, when I use the opposite x value, I have to have the same y value, so this also has to be negative 4. Okay, the same thing here when I have x is negative 2, y is negative 5, so when I go from negative 2 and make it the opposite, positive 2, I have to have the same y value that I had before. This is negative 5, and then when x is 1, y is 6, so when x is negative 1, y is also positive 6. So if you notice, I have opposite x's, same y values. For the odd function, I have right here at x equals negative 3, I have y equals 2. So when I go across the table to x equals positive 3, that's opposite x, I have to have the opposite y value, I have to have negative 2. This is a negative 1, so over here has to be a positive 1, this is a positive 3, this has to be a negative 3. So you see over here I have opposite x's opposite y's in the second row of the table. Now I have to do the composition. The composition says first I have to do g, and then I have to do the f function. So when I start here at x equals -3, I'm trying to fill in this square right here. So I start at -3. I start at -3. I get 2. Then I go all the way to 2. F is equal to -5. So this result here is -5. I'm going to just tap it with my stylus. -2 becomes 1. 1 becomes 6. -1 becomes 3. 3 becomes -4. 0 becomes 0. 0 becomes 2. 1 becomes -3. -3 becomes -4. 2 is -1. -1 becomes 6. And 3 becomes -2. And -2 becomes -5. So that is the last row of the composition h, which is h equals f of g of x. So I have to ask myself, is h even, odd, or none of the above? Well, if I look carefully, I have a nice little symmetry going on that my h of -x is equal to the h of x. Therefore, it is even. Is this always going to be the case? Well, yes, because let's make up an example. Let's say g, the odd function, is x cubed, and f is an even function, x squared, and we want to do the f of g of x. So f of g of x will equal f of x cubed, well, that would be x cubed squared, which is x to the 6th. So an even function is pretty strong. It kind of overtakes. So h was even because I had opposite x's, give me the same y values, and I showed you that when I do an odd inside of an even, I'm going to get an even result. So for the above problems, the above functions, I needed to take the domain of each of them, and I'll show you what the domains are. So for each functions, I did the domains. The first function, x plus 2, there's no restriction. The second function, x can't equal 3. And the last function, x has to be a non-negative or greater than or equal to 0. So when we do compositions, we're going to look at the domains, and domains only get smaller. They do not get larger. So when I do the composition, it's a function inside of a function. So for the first example, I'm going to try to keep what I have here. F has to go inside of g, so it becomes g of x plus 2. And now x plus 2 has to go in for the x in the g function, so that is going to be equal to 1 over x plus 2. That's the input. Don't forget the minus 3. So my final result is 1 over x minus 1. That is the composition of f inside of g. Now I have to pay attention to its domain. I notice there's a denominator here. So x minus 1 cannot equal 0. X cannot equal 1. So my domain is -infinity to 1 union 1 to infinity. That's what I get for a domain for that function. Second function, I have to do the f function into the h. So I have to do f first again. And I have h of x plus 2. I plug that into the h function, and I get it equal to the square root of x plus 2. Now I'm going to do my domain, which I have a square root. So I can use my square root rule. X plus 2 has to be greater than or equal to 0, or x has to be greater than or equal to -2. -2 to infinity is my domain. Now this last one, we have to do f inside of h inside of g. So as we go along, let's look at the restrictions for every time we have a new input. So if I do this properly, it's going to be g of h of x plus 2. Right now my input is x plus 2, and right now there is no restriction. I can use all real numbers for x plus 2. No restriction. But then I'm going to plug this into the h function. I have g of the square root of x plus 2. And we just did that earlier over here in the previous problem, part B, and we saw right now our domain restriction is negative 2 to infinity is our domain restriction. And that restriction can't go away later because I do other things. I've already established after 2 steps that my domain is restricted to negative 2 to infinity. Now I'm going to plug this x plus 2 into the d function and put it into the denominator. And when I do that, I get this whole thing is equal to 1 over the square root of x plus 2 minus 3. And that is my composition. This is what I have for my result of putting f inside of h inside of g. Okay, I'm going to focus on this right now. And I realize I already have a little bit of a restriction that I've done. I already have. I'm restricted my domain in part 2 of the problem. My final problem, I see I do have a denominator, so you have to take the whole denominator. This is the whole denominator, the square root of x plus 2, then minus 3, and that cannot equal 0. I'm going to add 3. I'm going to square both sides. And then I'm going to subtract 2, and I get x cannot equal 7. And I think you see that 7 is part of that window. So my earlier domain restriction of negative 2 to infinity has an extra restricted added to it that x cannot equal 7. So my domain for this final result here is negative 2 to 7, parentheses union, 7 to infinity. And I understand this is a little bit harder, but this is what we're trying to work on. So for the last problem, I'm doing decomposition. I'm trying to figure out what functions I have to put together in a composition to get the final result that I want. And order does matter. So again, it's kind of like working in reverse. So instead of going from the inside to the outside. So what I want to get is this final function. In part A, I want to just use 2 functions. In part 3, I maybe want to do a composition of 3 functions. So when I see this, f of g of x, I know g has to be first. So to me, I should look at the inside part of the function. What is inside this function I should do first? And what I should do first is the square root of 2x squared plus 1. And then I take the result and plug it into the log of x. And if you notice, if you take this and put it in for that x, you get what you want. That's what we're trying to do. Decomposition, breaking it up into what I call pieces parts. First piece is the square root of 2x squared plus 1. The second piece is the log of x. Now I can do the same thing, but maybe break it up into 3 functions. So I'm still trying to get this, but when I see this, I know p is first, n is second, and m is the last. So maybe my first piece should just be 2x squared plus 1. And then I plug it into the square root of x. And when I do that, I put that in here, I do get the square root of 2x squared plus 1. And I can take that piece and plug it into the log of x. So when I take this piece and plug it into the log of x, I do get what I want. I do get the log of the square root of 2x squared plus 1. Just something to think about. It's about how can I work, compositions working in one direction isn't so bad. So I relate it to driving. Driving forward is a lot easier than driving in reverse. Doing math in the forward direction is a lot easier than doing math in reverse. But we have to develop both methods.